Okay, so we continue to talk about some tips for training deep neural net. And this tip, we'll talk about adaptive learning rate. Okay, so we see it's a head map again, the show the gradient. Okay, so you see. So first, now we are here at this position, and you find gradient direction. The towards here. It looks very steep. Okay, so here you will get a very large gradient because here is very steep. So towards this direction, right? Okay, so at this time, at this moment, since you have a very large gradient, so if your learning rate is too large, maybe you will. Here, this one is your gradient. At this position, theta 0, and this is your gradient. Your cost function, and we will find gradient here, and then multiply with the learning rate. Then we will jump to here. You see, is this good? Do you think it's good? No, not good, right? Because you jump to a higher position. Your arrow is getting bigger. Right? Because if you jump too large, that's because your gradient is large and your learning rate is also large. So you may not decrease your cost. So it's not good. And at this moment, we should use small learning rate. Okay. So for the how about it? So we use now. Okay. So we use a smaller learning rate here. So here you see. It's multiply our gradient multiply with our learning rate. Okay, now it's getting smaller. Okay, so we do a very small step. If the step is very small, you will take more time to get converted, right? So here, this one is our ideal position. If your moving step is very small, you will get several iterations to reach the local minimum. Okay, still not good, right? So how to? So your learning rate is too small, the training will be very slow. Okay, so it's very difficult to choose a suitable learning rate here. And this time introduce a approach called adaptive gradient, called alpha gradient. So alpha gradient is the idea like this. Okay, so you see our original gradient is the function is formulated like this. Here is your next weight, the t plus 1 weight. And how to update it? You just use your current weight minus the learning rate multiplied with your gradient. Here is the gradient. Okay, it's a conventional gradient descent, the original gradient descent equation like this. So the other grade is just do a very small modification here. It adds one more parameter called sigma. So the sigma is updated for every iteration. Okay, so and the sigma, how to calculate obtain the sigma? You see the sigma is like this. The t means the t iteration. Okay, so and the t iteration is the sigma t can be calculated like this. It actually is the gradient, the square, and multiply from the first time to a t, from the first iteration to your t iteration. Okay, there's the sum of the square, and then we have the square root, and assigned to the sigma. Okay. So what is the suppose? Okay, so actually you see, so this process, if your gradient is larger, then your sigma will be larger, right? And we put it in here, in the denominator. It will make the overall ratio to be smaller, right? If it's smaller, if your gradient is smaller, then your sigma will be smaller, and here your totally overall ratio will be larger, just like this. Okay. So you just try to balance your overall learning rate. Okay, so you can modify the equation. You created this equation like this. Here we replace. Here we use the denominator like this, and you can see. Suppose here, if your gradient, your first time, your gradient is just very small, 0.1, 0.2, so it's the first iteration. And after the second iteration, you have to summarize the first gradient and the second gradient. Summarize the square together, then with the square root. And you see, through this process, your overall learning rate is becoming is getting smaller, right? But how about it? In this case, your gradient is 20. Then next time is 10. Okay, so you can follow the equation. Your learning rate will reduce. The first time will be like this. The second time you will have to summation of the first time and the second time to obtain it. So you see, in this case, your learning rate is also getting smaller, right? But since here, in this case, your gradient is larger, so their learning rate, their overall learning rate will be smaller. But in this case, your learning rate will be bigger than here, because here your gradient is smaller, so I will give you a bigger learning rate. For this case, your gradient is larger, right? So I will give you a smaller learning rate. Okay, but for both cases, we will just decrease the learning rate overall. Okay, basically, after several iterations, we expect you are getting more and more closer to the local minima. So you should use a smaller step to reach the local minima. So that's why we usually we make the learning rate getting smaller. Okay. So some observation, I have mentioned the learning rate smaller, and the smaller gradient, larger learning rate, and the vice versa. Okay, so it's very easy idea called adaptive gradient. Okay, any problems? Okay, so here you see. For example, here, if your direction, at this position, your direction, gradient direction is towards it here. Here is very steep, so we should use, since it's very steep, its gradient is very large, so we should use the smaller gradient so that it will not drop to another hill. Okay? And how, if you are at here, your location is here, and your gradient direction is towards here. You see, it's very flat. It's very flat, not steep. So you should use a larger learning rate. Okay. very simple.
There are some other variants.
For example, alpha grade, alpha delta, alpha m, alpha secant. Okay. So, but all of them are the concepts are very similar. Okay. So, any problem? And now we will talk about the next tip, called the dropout. Okay, dropout is also a very interesting idea. Well, the idea is like this. So here we have our network architecture like this. And each time, before you compute in the gradient, each neuron has p% to be dropped out. Like this. Okay, so suppose we have 50% to be dropped out. So here you can see the 4 neurons, there are 2 are dropped out. Okay, for this pair, there are 2 drop out. Here, 2 drop out. Okay, drop out means we just remove them in this training. We don't use these neurons in the training. Okay, so it's called a drop out. Okay, so when you remove these neurons, you see, your network will become thinner, right? You see the difference? We just remove this neuron and their network, so you have a thinner network. Okay, so the structure of the network is changed. We will use the new network for training. Okay. Yeah, but you will think why we just drop it and the others are not important. So we will not use actually we will for each mini batch we will reset for the dropout neuron. So remember the mini batch. We will divide your training data into several batches. For each batch, you just use them to update your weight. Then use the updated weight to take the next batch to train again. Like this, it's called a mini batch. So for each mini batch, we will use a different drop-off network to do the training. So, okay, so in your testing, let's just for training. So how about for testing? In your testing, you will use the complete network. And then, so if you use the dropout rate, you can set up the dropout rate as a training, suppose it's a p%. Then, when you use the whole neuron, all the weight should be timed with the 1 minus p%. Okay, so suppose that the dropout rate is 50%. So, if you use the 50%, actually there will be just a half of the original of the original network, right? And here, then in our testing phase, we will use the complete network. So if the weight W is 1, suppose this line, this neuron, this thing, the weight is 1. We should multiply with 1 minus 50% to obtain your final weight for test. So 5. Okay, I will explain it later. the intuitive reason. Why? Okay, so you see, here is, suppose you remove some neurons. Okay, this Chinese character. Okay, can you read it? 我的 partner 会摆烂，所以我要好好做。Okay? It means that, okay, you can treat each neuron. They are friends. Okay? They are partners. But some partners, they are very lazy. They don't do anything. Okay, so you know your partner, two of them, they don't do anything. Okay, so you know some will be do it better, do nothing, do nothing. Okay, so you should do it better. I should do it, work very hard, so that otherwise I cannot complete my work. Okay, so our work, I cannot complete our work because if our partner they fail, then I have to do more. Okay, so that's why if we remove them, it will be train station. Okay, so it's the idea called the main idea of the dropout. Okay, here is the explanation. When the team's up, if everyone, in fact, the partner will do the work, nothing will be done finally. Okay, so however, if you know your partner will drop out, you will do better. Okay, so when in your testing, no one will drop out actually, right? In your testing, you will use the complete network, so no one will drop out, so you will obtain a better result. Okay, so understand? So the idea is very simple, but it's really work. It's really work. Okay, any problems? Okay, so it's very easy. You just need to set up. For example, use the TensorFlow or Piano, such a deep learning library or toolkit. You just need to set up the rate you want to drop out. Then this toolkit will do it automatically. Okay, it will do the mini batch and do the drop out for you. You just need to set up the parameter you want to use. And then next I will explain why the weight should be multiplied with the 1 minus p%, the dropout rate when testing. Why? Okay, so the reason is also very simple. So when you are training, assume your drop rate is 50%. Like this, you see, four neurons and 2 are drop out. Okay, like this. Then when we do, then we will do you see the training. You see your code. You will calculate the code just by using the W1 and W3, right? So only the weight you can adjust is W1 and W3, and the code, have to be set to W1 and W3 for them to adjust it, right? So you just have to your total error have to be spread just to neurons, right? Okay. So at that time you will receive just 2 to modify their weight and not 4, right? So you will receive a stronger gradient, right? Because they are just only 2 to be adjusted. So the error propagates to the 2 neurons. The gradient would be very stronger. If you have 4 neurons, you have to spread your arrow to 4 neurons. So each neuron will receive a less gradient, right? So they will not receive a very strong gradient, so their adjustment will be very small. Okay, so in this case, you will receive W1 and W3 to receive the arrows, and the gradient will be stronger. Okay, so in your testing, how about in testing? In testing, no more neurons are dropped out, right? So they will also, through such a process, every neuron will get a, double stronger gradient to adjust their weight, right? So when you're testing, all the neurons are work together. No one is dropped out, but their gradient in training is double. So now they will contribute. It's also double. Their contribution will also double. Okay, so you see here W1 will provide a more stronger weight than if you use and here. So the training W1 and W3 will, after the training, will get a stronger weight adjustment. And when you are testing, if every neuron, every weight contributes a double weight, your Z prong will almost to be 2 of the Z here. So that's why we should separate. We should multiply with the dropout rate, 1 minus the drop rate here, to separate, to decrease their weight. Okay. After every neuron, their weight multiply with 0.5, you see, the Z prong will approximate to a Z. Okay, so it's the main idea. Okay. Okay. Is it clear? Yeah, I think just use your intuition to think about it. Okay. 可以吗？这样了解吧？ Okay, the dropout is kind of the ensemble learning. So what's called ensemble? Ensemble means I have several machines. I have several classifiers. Okay, and each classifier, okay, you see, when you use the training set is divided into 4 parts. And each set I will use a different network to do the training. Okay, so actually I will apply 4 different networks. Okay, so it's called just looks like the mini page, right? And then in your testing, your test data will feed to the 4 networks, and each network will output their result. Here, then we will do the average. It's called ensemble. It's called ensemble learning. We will train several networks, and then each network has their spatial skill to do the classification. And then here we will output the result, then we will average all of the results to be the final answer. Okay, so it's called ensemble learning. The dropout is just kind of the ensemble learning. Do you agree? Yeah, you see? You can divide the training data into 4 batches. For each page, we will randomly drop out some neurons. Okay, so for each page, we will use different network. And this, then in your testing, we will use, actually we will combine all the 4 different networks together, right? Actually in testing we don't drop out anything, but the training will separate the training for each different network. So when they combine together, it looks like an ensemble learning. The idea is very similar. Okay, so actually we will use 1 mini batch to train 1 network. So here, we totally will have 4 networks. And also you can see some parameters in the network are shared. Okay, so you see these 2 are shared with the same. Right? Yeah. Some neurons will appear in some network. They are shared together. But their shapes are very different, right? Okay, so when you're in your testing, testing data will actually, it looks like we feed the testing data to different networks, and then we average them together. It's actually equivalent to when we use the complete network, and we all the way multiply with the E minus P set. Then we produce the result is very similar to the average, very close, approximate to this architecture. Okay? So we can treat such a dropout framework is actually can be treated and can be regarded as an ensemble learning of multiple different networks. Okay, there are also some related research to discuss the dropout. Okay, so dropout generally works better with make out and make out. Okay, so combined with the make out, the dropout can perform better. Okay, so there are also some variants, but the best idea is like this. Okay, so any problem? No? So until now, I think all idea is all these tips are very simple, right? Their basic concepts are very intuitive and very simple. And you just need to apply your background, your fundamental background of the neural net. And actually, the neural network is very simple. So it's not very difficult. Actually, it's not very difficult to learn the neural net. Okay, but if you read the paper by yourself, it's really very difficult. Okay, so I think the Professor Lee is an expert in this area, so his slide, I think his slide is very good for you to introduce the neural net. We just give many details here. I just want to tell you the best knowledge so that you can use the neural net or the deep learning toolkit very well. As you know, what's the terminology, what's the function, what's the effect of when you apply this function. You just need to know this, and then you can prepare to build your own neural net. Okay. Now next we will talk about the final part,
the neural net with memory.
Okay, so for a neural network, sometimes it needs memory. Right? So here is an example. We show the input and output are sequences. Okay, so here is the input. Input is a sequence of the word, a sentence, right? The president of Apple is an apple. And the output is like this. The output will tell you a result of each word. And this case is called a name entity recognition. Name entity recognition is a test that tries to detect the name entities, like the name of the people, location, organization, in a sentence. So here is a sentence, is your input. The output will tell you this is for example, an organization or not. Or for example, here, it's not a name entity. Okay? President, no, it's not. Oh, no, Apple. Yeah, Apple is the organization. Right? It means the Apple company. And this one is, no, it's not a name. And no, Apple, yeah, it's a name, but it's a company. No, it should not be a company, right? It's a food. Here should be a food, right? So, how do you do such a recognition? Actually, you will need to refer to its previous input, right? You cannot just based on this word to do a recognition, to do a name entity recognition. You have to determine it by its context. For example here, you have to know what is the previous word. Yeah. Sentence structure. If the last one is still, if the answer is not, maybe because they have to know when appear in Yeah, I want to know which word is the name entity. It's a spatial name entity. I want to know. So here in this case, the apple is a name entity for organization. Yeah, I want to know which is the name entity. Yeah, so actually you have to know the grammar, actually the semantics of the sentence. You have to know the semantic information. Maybe you have to know the grammar, the structure, and to know the semantics of the sentence. So you cannot determine it just by this word. You have to need the memory of its previous word to do a recognition. Okay? So in this case, we say the DNA is memory. Okay, so here is a very special network called recurrent neural network. It's a network with a memory. We call it the RNN. Okay, so the value are stored in the structure. The framework looks like the infrastructure looks like this. So it's our original network. Okay, you will see layers, right? Here is here are input and output. Everything are the same, but we add memory here. So the memory will have a link to a neuron. You see? Here we have two memories. Okay, so each memory will have a link to the neuron. Okay, do you see? So memory can be considered as another input. Okay, so ARM works like this. Here's that. So our input S1, S2, S3. 1, 2, 3 means the time step. So the first one is the S1. Okay, so S1 is your input here, and so our new network multiply with Wi. And also, at the beginning, your memory is 0 at the first time, because there is nothing to remember. It's the first time, right? So first is a 0. So 0 multiplied with a weight. Or remember, it's just treat it as another neuron, another input. So the input will multiply with WH and summarize with WI like this. You see? WI multiply S1 plus WH multiply with 0 because the first time is 0. Then is your output. Okay, the sigma is the activation function and your output is A1. Then A1 multiplied with W0. Then we use the softmax to output your Y1. Okay, so Y1 is output here, given X1 at the first time step. Okay, next we go to the second timeline. The second time step. Okay, so I forget to remind you one more thing. You see, here we compute the neuron value. The output is A1 for this neuron, right? So we will copy the value A1 to the memory to remember the output of the neuron. Copy to here. Okay, it's just to keep a memory. Okay, so at the second time step, here your input is X2. Okay, so X2 multiplied with WI, your weight. And now the memory now is those A1, right? So A1 will multiply with the WH. So to form this function, you see WI X2 is here, and then plus with WH A1 is here. Then we will output A2. A2 will copy to the memory to replace A1. Okay, so they will continue to compute the output Y2 here. Okay, we continue this process. So next input is S3. S3 multiplied with WI here, and the plus with WH multiplied with A2. Okay, so we generate S3 and copy to your memory. Then we continue to compute Y3. Okay, so just repeat such process again and again. Okay, so another flow chart to represent the RNA. You see, in the initial, your memory is 0, and your weight is O is WH. So you see, so this process, we will generate A1. A1 will copy to your memory. Here you see a copy, and the A1, this memory, the A1 will be used for next time step to produce the Y2, right? And then A2 is copied to the memory again. Then we will use A2 to help to generate Y3. So each time you out your result, you will use your memory. The memory will contribute to to the output, right? So that's why why should we use the same network? Use again and again, and your output y3 is actually depend on your previous result. It depends on S1, S2, S3, also also the A1, A2. A1, A2 are just from previous result S1, right? So we just use this mechanism to match the output to have the memory, because the output is generated by using S3 and the previous result A2, right? The A2 is generated from S2, right? And the S2 is generated from the A1. A1 is from the S1. Just use it. So that the output always has the memory of the previous state. Okay, any problems? It's the basic idea of the RNN. 有什么问题？这样都可以了解吗？可以哈。Okay, any problem for you? It's okay. Okay, so I think it's just a simplified another framework of the previous slide, very similar, right? Okay, just like this. Actually, you can when spend it's the first timeline, first time set, the second time set, the third time set. But at each time set, we just use the same network. Okay, we don't change the framework, we don't change the network. We use the same network again and again. Okay. But the difference is the parameter. The memory is different. Okay, at each time step you have a different memory. Okay. But such a network is very difficult to change. It's too complicated. So in the training phase, so there are very smart researchers. They develop such a back propagation through time, called BPTT. BPTT is the idea to do the back propagation. Okay. No, the best idea is very similar, but this time we add one more, the weight for your memory. Okay, you have to change. You have to tune your weight of your memory here, WH. So you are not only to just W0 and WI. Also, you have to change the weight from the memory. Okay, so the chain is getting more complicated. So of course, it can be deeper, and it can be very deep, like this. See, we have many layers. Each layer has their memory. And here's another one called a bidirection like this. Also getting more and more complicated. Okay, so here is another test. Another test is going to do the speech recognition. Okay, so speech recognition like this. Here our input is the signal, the audio signal, and the output will be just a character. So the character sequence is much smaller than the signal. Okay, so it's although it's many to many, but the output is short like this. Output is just two characters, and your signal. Your input is audio signal is much longer or much bigger vector. Okay, so we can apply such an RNN in speech recognition. So like for example like Siri or the Google Assistant, they all apply the very advanced speech recognition. So have you ever tried Siri? Also it's very good in your for recognize your Thai language. It's good enough. It's very good. Okay. So that's okay. Okay.
It can answer.
Oh really? But how about the recognition rate? Is good or not? How about Chinese recognition? 你们有试过吗 ？Siri 啊，或者是 Google 的那个 Assistant 有试过吗？辨识效果怎样？啊，还可以啦哦。你们用觉得还不错啦哦。我用过觉得哎好像也蛮不错了哈。大致上大概是那种6、7成吧，哦，也蛮厉害的。I think it's very good for Chinese speech recognition, and maybe 6 or I don't know 50 or 70% accurate. It's very good, much better than 10 years before, than 5 years before. 5 years ago, the speech recognition is the performance of speech recognition is very, very bad. Yeah, but now it's much better. Okay, so the speech recognition, I don't break now. I will continue to finish because this is just the last part. I will finish that and then we will end today's talk. Okay, so I will not break now. Can you see? Can you read the Chinese character? 好棒，好棒，好棒棒。Okay. Okay, so actually you can see every signal you just chunk. You just segment the signal into several chunks and feed into your element. It will out the result. And some are the same. For example, you say 好棒, or maybe some people say 好棒. They're just the same characters, but you should trim. You should just remove the repeated words, repeat characters here. So you will do some trimming here to output your final sequence. Okay. But there's a question why can it be 好棒棒? 好棒棒. Okay, so how to solve this problem? Because based on this, you will just trim the same characters here. But if I say the words are the double the same word, how to solve it? Okay, so here we will use an extra symbol. It's actually the null symbol, empty symbol. Okay, so if your signal is actually 好棒. Okay, so the output will be 好. Okay, and here we just use the null symbol to remove the repeated character. Next one is 棒, and the other four are also 棒, but we will remove them. But if you talk about 好棒棒, okay, we will try to generate your signal, your audio signal like this. Okay, so the idea is like this. If you are interested about it, you can refer to the details. I don't know because the Professor Lee don't mention it in this slide. So actually I'm not an expert in speech recognition, so I don't know much detail about it. But they have tried to address such a problem. so there's another test called machine translation. Machine translation is also from many inputs to many outputs. And the sequence to sequence learning, or sometimes refer them as sequence to sequence learning. For example, here, machine translation like to translate the English to Chinese characters. Okay, so machine learning as your input and our output. The output should be okay. Here, the machine should generate machine learning. Okay, based on the two characters, I should generate Chih-Yi, and 学习. Okay, I should translate the sentence into another sentence, from an English sentence to Chinese sentence, called machine translation. So we can also use the argument to do the machine translation from many sequence to many sequence. Okay. So now I think the Google Translate just applied a similar idea. Okay, so they have planned. And remember last month, Google just announced they have built a more powerful machine translation tool, so that their translation can be much better. I don't know if everybody uses the newest version of the Google Translation. I'm not sure. Before you see the Google Translation, somewhat. Well, I think it's better. Actually, I think it's the state of the art. Its performance is state of the art, but the quality is still not good enough. Before for example, I see some students' homework, and when I see some very strange, it should not be a well-trained student can write such a very stupid sentence. It should be, I think, it should be translated from the machine. So for such homework, it's very easy to recognize. It's just a copy from the Google Translate. Okay. So for now, I'm not sure. Maybe this time, teachers have to spend more effort to clarify the translated or not.
Okay, so many to many, okay, to do the machine translation.
Okay, the problem is you have to know when to start the translation. Here, you see, 机器学习. Okay, here we should stop because we just input the two English. We just input the two English words, right? And then we stop. So your translation should not be continuous. We just start 机器学习, then stop. It's called it's a symbol called we just stop here. If there is no more input sequence, you should not stop here. This is just tell you when to stop to do the translation because it's a many to many, sequence to sequence. So even the input sequence is a null, it's an empty, they will still generate the output. So you have to tell them how to stop it, when to stop it. Okay. So RNA is actually very powerful to deal with such a, like a sequence, to process the sequence signal, like For example, your document. Your document is just a sequence, right? To do the machine translation or to do speech recognition, your audio sequence. So it's very powerful tool to deal with the sequence, to output, to generate from your input sequence to your output sequence. So it's very powerful framework. Actually, the performance is not very good because it's too complicated. And they find when so the idea is very good, but in practice, for the real application, the performance is not very good, actually. So there's some reason. So for example, the error service is very long. You add one more weight to change your memory of the weight. So it's very difficult to change. And also, you see here you see the example here. Since the memory will keep, right? Will keep the memory. So if your weight, suppose your weight is 1.01, like this. So after 1,000 times that, and 1,000 times that, your weight will become 20,000. The weight is multiplied again and again. So it will become like this. If your weight is just 1, so after 1,000 iterations, your weight is still 1. Okay, but it's not like this, just only a small one, 1.01. After 1,000 iterations, after 1,000 times that, it's getting much bigger. How about if your weight is like this? It's very small, and not very small, just like 0.99. After 1,000 iterations, it's almost a 0. So you see, for a large gradient, if the gradient is large, okay, so actually you should apply a small rate. And if your gradient is small, you should use a large rate. So the best idea for the other grade, right? Adaptive gradient we mentioned earlier. But it's not such a easy test. Okay, so you see, actually if your input sequence is at 1,000, at 1,000 like this. So after 1,000, your weight will have such problem. It's not very easy to adjust it just by the the adaptive gradient. Okay. So there are some remedies. Okay, so you can use the advanced momentum method to improve your gradient descent. Okay, the technique to apply the gradient descent to improve the gradient output, the gradient. Also, some RS is the advanced other grade. It uses the second derivation change. And the next one is called a long short-term memory. It's abbreviated as LSTM. It can deal with the gradient range problem. Okay, so now it's the most popular framework currently to address the RNN problem. So the long-term and long short-term memory architecture looks like this. Okay, but I don't want to talk it now. I will leave it for one of our students to introduce the knowledge. Okay. So if for the students who choose the RNN, you must address LSTM. Okay. So LSTM also has a memory cell, and also very interesting is with the forget, or just to simulate you have a memory, but sometimes you will forget. So you will forget something, right? So use the memory and also forget. Okay, if you forget this, the memory should not be output, should not be as the input. Okay, so there will be a very interesting technique in LSTM. Okay, I leave this part for our smart students. Okay, like this. Okay, so I just give. Okay, so finally I talk about the next way for deep learning. Okay, there is a new model called the attention-based model. But actually I cannot figure out what is going to talk in this. So, sorry, I can leave to you. Okay, concluding. Concluding remarks. Okay, here we spent 2 weeks to introduce deep learning, and we discuss some reasons using deep learning and some tips to train your deep neural network, like RELU, max out, drop out, and RNN, LSTM, and so all the necessary terminology you have known, and their basic idea, the intuitive concept I have introduced to you. Okay, so thanks for your attention.